All right. Okay, it's working. Sweet. Okay, guys. We got cut a little short last time, so let's clarify something here. So, if you have a position function. Okay, position function a lot of times will be some function like x of t. A lot of times you're talking about a particle moving along an x-axis. It could certainly be y of t, something like that, but get the idea hopefully. So this would describe, for our purposes, most of the time it'll be some particle or an object traveling along some x-axis. It could be like a little car or something, however you want to think about it. But basically what this would be is the car's position depends on time. Okay, so then how about velocity? Well, the velocity function is just the derivative of the position function. Okay, so that's the instantaneous velocity function. Okay, so think about what that means. The derivative is, so it'd be the change in x over the change in time. Now, if you think about this equation, that's a lot like saying the average velocity is the displacement over the time period. So take a second and think about that. Make sure that makes sense to you. So if I want to talk about some overall time period, okay, say it was like a 2 or 3 second period, and I know where I started and where I ended, I could just divide the displacement, right? The displacement being the difference between my starting and ending positions. I can divide that displacement by the total time and I get the average velocity. But if I want the instantaneous velocity, so say I want to get the velocity right at some specific time value, then it's just, instead of being a big delta x over a big delta t, it's an infinitesimally small dx over an infinitesimally small dt. So are there any questions on just that connection there between like this statement and this statement, or does that make like intuitive sense to you guys? Okay, so if you think about units, I'll put some units comments in like blue here. So think about units, like, well, let's say the units of this function was meters. Okay, so suppose that this road or whatever, this axis was marked with little like meter markings. How many meters are you? Like a meter stick, or a really long meter stick. What are the units here of, a change in position? Well, your position is meters, so you'd be talking about meters over whatever the time was, whatever you're measuring time in. So, like in physics, a lot of times it's science in general. We usually use SI units. So meters, seconds, meters divided by seconds would be your velocity. Now, there's nothing stopping you from going like feet per minute, or if you were a snail, inches per hour, something like that. Make sense? Okay. How about the next thing? How about acceleration function? What is acceleration? Well, I'll give you a definition of average acceleration. So the average acceleration is the change in velocity. Is everything okay back there? What's the matter? Good? Okay.
I'm thinking about different units of time. If we like instead of miles and like kilometers, time was like not regulated. Like no, anyway, it doesn't matter.
Well, those are distances.
Different measurements.
Like miles and kilometers measure distance.
Yeah, but what if people just thought about time in different ways anyway?
Oh, okay, yeah, like you, right. So like if time was.
So you don't have to think about it.
Well, like if you, yeah, like why split up an hour into 60 minutes, that kind of thing.
Sure. Well, why not just like what if we didn't go by hours? What if we went by quarters of the day?
Right. Yeah. So why divide a day? Because it makes sense to make a day, right? Because the sun comes back to where roughly it was the day before. I mean, if you look back to like some ancient cultures, they'd go, okay, well, we kind of have this idea of the sun was there yesterday, and then the next after 24 hours. Now, it's an interesting question. Why split that up into 24 units? Because certainly you could just split a day up into like 10 units of time and call those blowers. Or dowers, I guess would make more sense because it's decimal. Anyway, the reason they tend to use numbers like 24 and 60 is because they're highly divisible. So it's the same reason why why are there 360 degrees in a circle? Is there anything stopping us from saying a circle it's 400 degrees? No. Anyway, what?
Who decided this?
Just humanity collectively. So like,
The drunk guy.
well, it's like who decides that the sound tree represents that thing out there? Like, no one like
Dude, I
decided
thought
that.
about that
It just
so
it
much.
emerged.
It hurt my head. Some guy.
God.
No.
Don't
go there. Don't go there.
There's a whole field of study where you can study things that are like called emergent systems. So it's like the best example is like an ant colony. There's no central control in an ant colony. No one decides what the ant colony does. Okay, so every ant is just following a very simple set of instincts that it's programmed to follow. But then out of that emerges this very highly complex behavior. So same thing with humans. Every human's just following pretty simple like parameters, reacting to things.
We're on this thing.
But well, yeah. So,
Moral of the story, we're all
but I mean, large scale though, something like language, you can think of language as being like an emerging structure out of like people. If we were like cavemen, I trying to like communicate we were trying to cooperate to achieve some goal together, and through that kind of thing, you can have like, people we kind of agree on things. So anyway, to your time thing, I think ultimately George, meet me at the cave tomorrow to hunt that, what are those things called? Woolly mammoth.
What are those things?
We'd have to decide maybe on some kind of like time to meet maybe. So maybe that could be like the genesis. But anyway, sorry, to answer your question is usually the 24 is divisible by 2, 3, 4, 6, 8, 12. Right? You can split it up into lots of different fractions. Huh? 60 is divisible by 5.
That's a real big deal.
So when you want to talk about, splitting an hour up into minutes, 60, there's 60 minutes. So that's divisible by 5 and 12.
That really made that conversation.
It was not for
5.
5. So
I was like,
anyway, so okay, sorry. So acceleration. If you think about what is acceleration, you never considered what that word means. It means when you change your velocity over some time period. So if you speed up or you slow down, that's called acceleration. Okay, and you quantify that by going, well, I'll give you a quick, very simple example. Let's suppose in my car I was going 10 meters per second and I sped up to 30 meters per second, and let's say that took 4 seconds. Okay, so what's the acceleration? Well, I changed 20 meters per second and it took 4 seconds. So the answer would be 5. But then the question is 5 what? Well, meters per second, right? Now, a lot of times saying meters per second is a little bit of a mouthful, so they just go meters per second squared. Why? What the heck's a square second? Well, you don't really need to think about it in terms of that. I mean, maybe we could, but well, it's just how fractions work. So m over s divided by s is m over s squared. In much the same way that, say, 3/4 divided by 4 is 3 over 4 squared. So there's nothing fancy going on there. It's just, you know what I mean? I just mean sometimes people get confused. They think this is some crazy, like, wacky thing. It's really just a shorthand, way of saying meters per second. So that makes sense? That the units?
Mm-hmm.
Okay, now again, what if it had been, where you got to be careful though is, last comment on this before we get back to the derivatives is like, what if I sped up from, say, I was driving 5 miles per hour and I accelerated up to 45 miles per hour over, say, whatever, 4 seconds. Now you gotta be careful with your units because the acceleration is 40 miles per hour per 4 seconds. So if you wanted to express that, you might say it was 10 miles per hour per second, but you wouldn't say miles per hour squared because you're not dividing miles per hour by hours. That still makes sense? Okay. All right. Now, usually in physics, you don't have to worry about that. In calculus, they typically are going to give you, it's going to be like meters and seconds or feet and minutes, and it's all going to be the same unit, so you don't have to worry about it too much. So anyway, acceleration is, so what do you think I'm going to write right here then, based on this definition?
Velocity prime equals.
V prime.
That's it.
Right? So there's a chain reaction sort of happening here. The derivative of position is velocity. The derivative of velocity is acceleration. And of course, I can also write that as dv over dt. Does that make sense? That the analogy here?
Mm-hmm.
And then, like I mentioned yesterday, just for fun, this is all you have to know here, but it is kind of interesting to think about, well, yeah, what would come next? Can you just keep taking the derivatives, theoretically? Yeah, you can go jerk, would be the derivative of acceleration, then you go snap, then crackle, and then pop. And you could even, nothing's stopping you from keep going, but as far as I know, there are no names beyond that. So, and of course, yeah, just to clarify, the units would be meters per second. That's squeaky. All right, so now what does that tell you? If you're looking at a graph, for example, let's say you're looking at a velocity versus time graph. How do you find acceleration from a velocity versus time graph? The derivative, also known as slope. Just look at the slope. So where's the one we got kind of cut short on? So was it 2? Or was it? It was 3. So number 3 on our problem set, at time 1, the velocity was 3 meters per second. Don't forget the units. And the acceleration was also 3 meters per second squared. Because the slope at 1 is 3. Everyone okay with that?
Wait, acceleration at 3a would be 3,
Say that again.
Well, no, at time 1. Did I misspeak?
No.
I'll write on the board. Yeah, so we're gonna do A, B, C, D, E, F, just to make sure there's no confusion here. So here, so at time 1, the velocity is 3 meters per second, and the acceleration is 3 meters per second. So maybe that's a little confusing. It's the same number, but the answers are 3 for different reasons. This answer is 3 because it's the y value of the function. This answer is 3 because it's the slope of the function. So if we go over to now, how about at time 3 seconds? Well, now the velocity is 6. But what's the acceleration? 0. Because the slope up there at the top of that graph is 0. Okay, so there's part A, there's part B. Part C would be, how about at time 6? What's the velocity at time 6? 4. How about the acceleration? Negative 2. That is a word that gets used. We typically don't say like deceleration or deacceleration, but we want to say negative acceleration. It avoids some confusion because it's a lot more precise if you just say a negative acceleration. Because then there's things like what if I'm moving? There's certainly nothing wrong with saying it because like to me, I would think of this as being like what direction am I moving at this stage in the No.
Left.
No. It's moving right.
Oh, right, because it's forming left.
Oh yeah, let's make sure there's no, okay, I'm glad we went over this. So, look at the graph. Cap stuck on. So let's take our time here. This is this can be a little confusing here. So remember guys, this is not a graph of like the path of the particle. It's a graph telling us the velocity at any given time value. So like over here at time 6, this was time 6 that we're looking at, the velocity is still a positive number. It's positive 4. Now remember, we're moving along an x-axis. So if your velocity is positive, then your x value must be increasing. That make sense? So yeah, like if you're picturing, so I could definitely see someone being confused if you're imagining like the car traveling along this or something, because it's certainly tempting to think of it that way, but that's going to confuse you. So what you got to do is just look numerically. Yeah. So positive velocity means you're moving to the right. Now, what does it mean if your acceleration is negative while your velocity is positive? You're slowing down. So let's back up. What was happening at the original one? Was I moving right or left? Right, and I was speeding up. How about here? What was I doing? Very good. I was moving to the right, but I was just maintaining my speed. So that's a lot of time when you're driving. You're traveling with positive velocity, and your acceleration is 0. You're not really speeding up or slowing down. Okay, so doing the next one, let's do time 8. What's the velocity at time 8? 2. Very good. So I'm moving to the right again. My acceleration is how about at time 10? It's the same exact thing. So this is also happening when time is 10. Nothing has changed. And then lastly, at time 12, running out of room here, but over here at time 12, my velocity is 1. My acceleration is negative 1. All right, so if you visualize this, did he ever move left? No. He started at rest, and he accelerated up to a max speed of 6 meters per second. He maintained that max speed for about 3 seconds. Then he started slowing down until he hit 2 meters per second. He maintained that 2 meter per second speed for 4 more seconds, and then he slowed back down to rest over a 2-second period. So that's the saga.
He burned all his energy at the start.
Yeah, that's a good, yeah.
Really fast.
That is actually, yeah, it would be a good explanation if that was a person running, yeah.
Could you use this graph to like represent a car on like a windy road? Like if you make one direction, like say like went out right, and like he's traveling, and as he like turns a corner, does his velocity like it decreases in that direction? And so, yeah.
Well, in terms of like making a graph of that, you certainly can describe that. Like what you usually would do is, that's a really good question. So thanks for asking that. You mean like a velocity time graph? Yeah. Okay, so there's 2 approaches you could take. So let's say you're going to drive your car on this windy road, right? Well, here's the windy road. Here's your Le Mans. Okay, so there's your windy road, right? So one way to describe it would be, let's say you wanted to describe velocity versus time. What they would do, if this is a multivariable calculus class, you would say, I've got a velocity function, which would have, at any given point, your velocity would be a vector that has an x and a y component. So actually what you'd say there's velocity in the x direction and velocity in the y direction. So, like a vector, here's my velocity, here's his component in the x direction, and then there's a component in the y direction. And so what you would do is you'd say something like, you would describe the velocity as, you'd have two little expressions. You'd have an expression that's governing the x component, and it depends on time. So it could be something like 3t squared plus 1. And then your y component could be square root of t plus t or whatever, just making that up. And that's one way to do it. And then what you would do is you might create an animation that shows how that vector is actually changing over time, on a computer. Or you could even draw sort of like a collection of vectors along this curve, but now you're describing your velocity as a function of position. That's a little bit different. So anyway, you can do the answer to almost any question is, can you describe this thing mathematically? The answer is almost always yes. You can describe these velocity vectors. Does that answer your question? Or? Yeah. All right, so there's some more graphy ones. They should be pretty straightforward. If you get stuck on one, we can go over it in class, but people don't typically get too hung up on those. They should be pretty straightforward. But just last clarification, how would a velocity time graph tell you that the particle was moving left?
If it went below.
Yeah, if it went below the horizontal axis, then you have a negative velocity. Okay. All right, so we're gonna employ the first thing we talked about using some functions here. So we're gonna jump forward to number 7. Okay, so Caleb, your question actually is really interesting. You can think about, you could also.
Yeah, I was thinking about setting one, a direction as velocity, as v, and then having it, as it rounds a corner, it's going to be traveling faster in terms of velocity in the positive, and then as it turns away, it's technically going to be slowing down in that velocity. If that made any sense?
If you're focusing on one component?
Yeah.
Oh, yeah. In that the original one where you have a Vx and a Vy, you could certainly say, what if I'm only concerned, and say your curve was like this. So as you're rounding this, as you're coming around this corner here, you're like, oh, you're not really making any forward progress, are you? You could certainly graph the Vx value versus time.
Yeah.
And so for a problem like this, it would end up looking like, well, I'm making good progress here, so high value, not making so much progress there, and then making a lot of progress, and then not making so much progress. And so that Vx value would actually depend on, the shape of the curve.
Yeah.
It'd be hard to interpret that by looking at it. But anyway, sorry. So let's get back to number 7 here. But that was an interesting question, so thanks. Okay. Watch how, I think you guys will like this. They're actually very simple. So there's a position function. Okay. So, and sorry for being a broken record and all, but that's a parabola, right? Does that mean this particle is moving in a parabolic path? No. It's moving along an x-axis in a manner such that its position function is parabolic. So it's kind of hard to describe that in intuitive language. But I don't want you to have the impression that it's moving in a curved path. It's not. So it's constrained to move along this x-axis. It's just moving back and forth. Okay? What is the position versus time graph? Let's graph that. So position versus time. By the way, this might confuse you really bad. In the position versus time graph, this is time. What's this? Position. Might be upsetting because the vertical axis is the x-axis.
Oh, that's what you're getting at.
That always throws people off, especially if you just are given one of these, like say a test or whatever gives you, or a textbook goes, hey, here's this x versus t graph. You're like, wait a second, x is on the y-axis. What's going on? Well, this is describing the position of the particle along this horizontal axis. Okay, so how do I graph that? Factor it, yeah. So it'd be t. Everyone agree with that? Factorization? I know it's a parabola, but I don't know exactly where it is. So if you factor it, you know 1, 2, 3. You know that it's a parabola that crosses at 1, 3, right? Everyone cool with that? By the way, that graph right off the bat tells us a lot of interesting information about the, say, the velocity. Let's tell the story of this guy's velocity. What direction is he moving? Right, like in this part. He's moving left, right? Think about his position on this graph. He used to have big positive x value, and now he's having it be smaller and smaller, even go negative at a certain point. Then what happens at time 2 then? 2 being halfway between 1 and 3. You're trying to process too much information because it turns out actually this is constant acceleration the whole time. Just think simple. It's simple. He moves right. So the story of this guy is he's moving left, then he moves right. Is that fair enough? So in terms of velocity, his velocity is negative, and then it goes positive, right? Yes, Melissa?
So does negative mean they're going left and positive mean they're going right?
Mm-hmm. Yep. So positive velocity would mean you're moving to the right. Okay, so that's part A. Let's get part B and see if part B agrees logically with that graph. Can I get the actual velocity function without too much work? Yeah. 2t minus 4. That was pretty easy. Now I can graph that. Now that point is of interest. Where would this graph, now this is a time versus velocity graph. What number is right there? 2. Does that agree with this graph? Where, yeah, see how the velocity is changing from negative to positive? That's what we see. That's what we saw in the position graph. So, what you want to do is try in your mind try to think of the connection between this graph and why those connections are there. So, this 2 tells us that yes, this is where the particle is stopped for a very brief moment, right? As he changes from moving left to moving right. And we can also see that on this graph. Then part C, let's get the acceleration function. Just 2. So this is what I was talking about with a second ago. It's very difficult to look at the position graph and just instantly know information about, because this is really the second derivative, right?
Yes.
Because you'd have to go derivative. So we will get there eventually. We'll develop some techniques for sort of mentally translating between a function and its second derivative properties, but it's pretty challenging to get anything beyond. Long story short, eventually we'll be able to look at a graph like this and say the second derivative is positive, but we won't know much beyond that because of how curvy it is. It's called concavity. So, okay, now this graph is pretty simple, right? Boom. Acceleration equals 2. So this is what we call this is constant acceleration. Okay, so acceleration is the same the whole time. All right, so let's answer these questions. D, when is the particle at the origin? Remember, the original question is saying this particle is traveling back and forth along a one-dimensional axis. Again, this is why it's confusing. Two-dimensional structures are all describing one-dimensional movement. So you're stepping, kind of weird, you're stepping up a full dimension to describe a process, okay? Nope. Anyone else take a shot at this?
Zero, isn't
One and three. Very good. So that. Very good, Liam. So at time 1 and at time 3. So let's think about that answer. Why is that correct? So if we're asking the question, position at origin, what question are we asking mathematically? Very good. So we're asking we're saying at what time values is that true? We'll come back to your position versus time graph, and you can see, this is where Jesse's factorization would help us out, right? So we can see that at time 1 and time 3, the position is 0. When is the particle stationary?
T equals 2.
Very good. So the word stationary means that the velocity function is equal to 0. So there's our vocab of the day. So that happens when time is 2. Now there's 2 spots in our problem where we could determine that number. We could have looked here, or we could have looked there. And then lastly, average velocity and average speed. All right, this will be interesting. Which one of those is easier to calculate almost every time? Average velocity is pretty much always the easier one to calculate. Okay, so I'll do F up here. All right, so F. Let's get the average. There you go, Jesse. There's the average for you. Okay, so to get average velocity, all you do is get the overall displacement and divide it by the overall time. What's really convenient about that is you get to ignore like everything in the middle, right? There could have been a whole bunch of stuff happening between time 0 and time 5. You get to ignore it. So the displacement really, now tell me this, guys, does it make sense if I just read it like this? Position at time 5 minus position at time 0? Or does that look confusing? That might remind you of the average rate of change calculation.
Yes.
Like f of A minus f of B over A minus B kind of thing. Okay, so what was the position at time 5? 25 minus 20 plus 3 is 8. What was the position at time 0? 3. Okay. Did I do that correctly? No typos, right? Over time period of 5. So what's the answer to the average velocity? 1. There weren't any units really given, I don't think, so I can just say units. I guess we can just assume it's seconds. So that's the average velocity, 1 unit per second. What's this? Now, for the average speed, this is a little bit more complicated because I got to sort of tell the story of the particle. Here's my x-axis. Where was the particle at time 0? Position 3. And then what did he do? So he went from position, so come back to position versus time graph. He started at 3. How far left did he actually go before he came to rest? how could I figure out that that position value? Plug in 2, right? Everyone understand that? Why plugging in 2 would be the thing to do here, or is that confusing? Okay, so plug in 2, you get 4 minus 8 plus 3 is negative 1. So it turns out that he traveled to the left to a position of negative 1, and this is where he turned around. So he went this way, turned around, and where did he end up eventually? At time 5? Okay, who's lost? A little bit, so let's back up then. Was it the negative 1? Okay, so what we did was we said, so does it make sense why this graph is saying that he went left and then right? That does make sense? Okay. So does it also make sense why does it make sense why I know that this time value here is 2? And then does it make sense how if I plug 2 into this function, so, sorry, I'm running out of room here, but if I say, what was the position at time 2? It would be 4 minus 8 plus 3, which is negative 1. So what that tells me is that the particle started at position 3. So assuming we start the stopwatch at time 0, based on this function, time 0 he starts at 3. We see that at time 2, he's reached his leftmost position, which is negative 1. And then he starts moving to the right. And then at time 5, we plugged in 5 earlier and got that 8. So those all make sense now? So how far did he go? He traveled 4 meters plus 9 meters, or units, sorry. So he traveled the total distance of 13 units, and it took him how long? 5. So the answer to this would be 2.6 units per second. So notice his average speed is a bigger number than his average velocity because the average velocity took into account this negative movement and treated it as negative. Let me show you something here. Might help, especially if you're trying to figure this stuff out. Mr. Computer. Yes. Yeah.
So whenever it's going left, is the slope negative or is it in the negative y values?
Whatever what?
So whenever it's like going left, the velocity is going left, or is the slope negative or is it in the negative y values of the graph?
Oh, good question. So let's see. Going left. Let's write it down actually. So let's do going right versus going left. Okay, so going right would mean there's 2 ways to think about it, right? Either I can think of that as being like my velocity is positive, right? Now again, how do you know velocity is positive? If the graph is above the time axis. So like all this stuff here refers to going right. Going left means velocity is negative, which would be down here below. Or you could think of it as the slopes on the position graph, right? So if your slopes are negative, meaning if x prime is positive, you're going right. And if does that make sense?
Yes.
Did that answer your question?
Yeah.
Okay, so this is one of the tricky parts of calculus is getting this straight about going like, okay, if I'm looking at slopes of this graph, right? If this guy's slope is positive, we're going in the positive we're traveling for the positive velocity. So positive slope means positive y value on this graph. Yes, Aiden?
So you can only take the slope and say on, just for the positive going right, but you can only do that from position versus time graph, not any of the other graphs with the positive slope. But I guess, well,
Okay, correct me if I misinterpret the question, but like this, are you saying like, okay, the slopes of this graph tell us about the velocities.
Yeah.
Tell us if we're going right or left.
Yeah.
The slopes of this graph tell us if the acceleration is positive or negative. So if this graph, we'll get to some more complicated questions later, but like if this graph is downsloping, then the acceleration is negative. If this function, so it's a chain reaction. So it's like, so if a function is sloping up, its derivative is positive. If the function is sloping down, its derivative is negative. Now that also applies jumping from here to here, or from here to the next function. So generally, I could say, for example, if this might sound weird, but like I said, like if the 7th derivative was sloping up, then the 8th derivative is positive. Does that make sense? Okay. Anyway, I was just going to show you something. I got to maybe change my variable here. Because in Desmos, you can define a point. I can say, oh, graph the point 2, 5, and it'll graph a point. So I should be able to do something like a squared minus 4a plus 3 is my x value, and 0 is my y value, then add a slider that goes from times 0 to say times 5. And I can animate it, I can show the journey of this point. Wow, I laughed, I cried. But do you see what I'm showing you here? Let's slow it down a bit. Okay, so at time 0, where did the particle live? 3, 0. How about 1 second later? Sorry.
0.
Does that agree with our position graph over there? Okay, let me zoom in a bit. Let's go to time 2. Where should he be?
-1.
He's at -1. Does that agree with our position time graph in the far left over there? Oh, sorry for the stupid computer. Sorry. Okay, so what I'm showing here on Desmos, if you want to try it out yourself, if you're confused at all, is you can define a point like that, and then you just can't use an X or a T or anything because it'll think it's a variable. Just use like an A, and then you can animate it. You can watch the point actually live its life journey. Okay, so this would be a good way. I want you guys to solve them without a computer. That's the point of, obviously computer is a very good tool for this kind of stuff, but the idea is to try to like learn how to do them by hand. So as you go, boom, -1, and then he travels all the way back to the right. Notice he's speeding up, right? You guys see that? And by time 5, he's at position 8. I can go farther. I can go 20 seconds. Watch what's going to happen. Who's got a prediction of? By time 20, is he going to be going really fast or really slow? He's going to be going very fast. And then he's going to go faster and faster and faster and faster. And you can see he's, yeah. But there you go. So if you're finding yourself confused, count yourself lucky that you live in the era of modern computers that, this is a great tool for like making intuitive sense of all this stuff.
What is acceleration?
Well,
How would
a
you
professorial answer to that is, well, Rafe, it's the derivative of the velocity
Yeah,
function.
but like,
I'm just kidding. So acceleration is the change of velocity over time. So It would be like, Zeno famously said that motion is impossible. But you go, no, Zeno, you're not right. You can change position, right? So what does it mean if I change position over a time? That's called velocity, movement, right? Okay, let's extend that. Can I change my velocity over time? Yeah. What's that called? Acceleration. Did I miss the question? Did I not get it?
No, you got it.
Makes sense.
I guess I'm confused. So if the acceleration is constant at 2, like you said, does that have nothing to how does it sit down, I guess?
Oh.
I was going with acceleration of constant,
Yeah.
and then the speed was
Excel-
the same.
Right, that's why it gets a little confusing, right? So acceleration is 2. That means that, here, in case any of you guys have the same question. Okay, the question is, if acceleration is constant, why is it going faster? Well, what this means is, suppose it was meters per second per second. The way you interpret this number is, I'm accelerating at 2 meters per second of velocity gain per second. So if I was looking at, let's say, like, here's time, here's velocity.
Oh, so the more the time goes by, the more it kind
Yeah.
of adds on.
So let's say we start at 2. At time 2, the velocity is 0. But at time 3, the velocity would be 2. And then 4.
Okay.
And then 6, you can see, look, it's getting faster and faster and faster every second. So it's going to cover more and more distance each second. Does that make sense?
Yeah, now it does.
Sweet. Cool beans.